In this video, we'll be talking about function composition. So there is one more way to combine functions which is unique to functions. In the last video we saw arithmetic combinations, which you can still do with numbers as well. But here, this is something truly unique. So the composition of the function f with the function g is defined as f composed with g of x. And that is really just equal to f of g of x. So, really the way to think about this is it's sort of a function within another function. Or, if you prefer, functionception. And that is to quote the movie Inception, where there were dreams within dreams. So, just a bit of a joke to help you remember. There's a nice picture that goes with this, namely, if this was the domain of f, if this was the domain of your function g, this were the domain of f, and this were the, this is the range of f, then we have that the range of g should sit in here. And here, what happens? Well, g takes an element x over here to some g of x in the range. But then that gets sent over here by f over here to an element f of g of x. Just like g takes x to g of x. Okay? Two quick examples of this. We have here that if we had the function, if f takes 0 to 3, 1 to 1, 2 to 0, and 3 to 2, and g of x takes 0 to 2, 1 to 0, 2 to 3, and 3 to 1, then what would we have? We would have that 0, f of g of x, would be what? Well, first g takes 0 to 2, but then f takes 2 to 0. G takes 1 to 0, f takes 0 to 3. G takes 2 to 3, and then f takes 3 to 2. Then finally, g takes 3 to 1, f takes 1 to 1. Okay? Or another picture of the way to think about this is, if this is 1, 2, 3, and 4, if this is 0, 1, 2, and 3, sorry, 0, 1, 2, and 3, what we actually have here is, and this is 0, 1, 2, and 3, and then we have 0, 1, 2, and 3 over here. Then what happens? Well, g takes, we have sort of g gets applied first because it's on the inside, right? And so g first takes 0 to 2, then 1 to 0, then 2 to 3, and then 3 to 1. But then f takes, what does f do? F takes 3 to 1, 3 to 2, I mean, sorry. It takes 2 to 3, and it takes, no, it takes 2 to 0, sorry, I got confused. It takes 2 to 0. It takes 1 to 1, and it takes 0 to 3. And the way to think about this is then, for instance, if we want to find what f of g of 1 is, what we have to do is we say, okay, first apply g, takes a 1 to 0, but then it takes 0 down to 3. Thus we get that. So it's like the full path. If that's a bit too complicated for you, in practice this is a lot easier to compute. Namely, we have here that if we wanted to compose these two, f of g of x, this is the same thing as f of g of x plugged in. So let's write that out first. But that's f of 1 minus x, and that's a 1 minus x plugged into f. So 1 minus x squared, which if we FOIL that out is 1 minus 2x plus x squared. In case you haven't quite gotten the hang of this yet, let's go ahead and work an example. So let's compute each of these values. Here, we first have f of g of x. So here, we could f of g of, so this is, f of g of x, which we know is the same thing as plugging in, let's write it this way, as plugging in g of x into f. So that would be f of 4 minus x squared. But f just takes whatever we have and adds 1 to it. Adds 2 to it, sorry. So we'd get 6 minus x squared as our composition. Here, if we compose the other way, we end up with g of f of x, which would be g with with f of x plugged in, which now we just go ahead and what does g do? Well, it takes 4 minus whatever was plugged in squared. So 4 minus x plus 2 squared. Again, order of operations says we square first. 4 minus x squared plus, FOILing out, 4x plus 4. We now apply the multiplication by the negative. 4 minus x squared minus 4x minus 4. The 4's will cancel, so we just get negative x squared minus 4x. Here, notice that the composition does two different things depending on which way you compose g and f. More on that in a bit. Here, we have, so there's again sort of two ways. If you watched the last video, you know that you have an idea of how this works. There's sort of two ways to deal with this. The first method is to recognize that we already computed g of f of x, g composed with f of x, so we can go ahead and just plug negative 2 into that. That would be that g composed with f of negative 2 is really just negative 2 plugged into negative 2 squared minus 4 times negative 2. Again, order of operations is king. Negative 2, so we have negative times 4 plus 8. Negative 4, negative 2 is positive 8. So we just get positive 4. However, if you, for instance, hadn't computed this, what would be possibly an easier way to do this? Well, you wouldn't have to compute that. You could just say, well, this is g of f of negative 2. F of negative 2 plugged in is negative 2 plus 2, which is 0. So that would be g of 0. And then 0 plugged into g just gives me 4. So that's another fine way to do it. And now it's time to have you try an example. So given f of x equal 2x plus 5 and g of x equal 4x squared plus 1, find the following. F composed with g of x, g composed with f of x, and f composed with g at negative 1/2. On the count of 3, I will reveal the solution. 1, 2, 3. So here we see that the composition of f with g gives us 8x squared plus 7. We see that g composed with f gives us 16x squared plus 80x plus 101. And then again we have our two methods. Either just use the function the composition of f composed with g and plug into it directly, or evaluate slowly starting on the inside and working your way out. So negative 1/2 plugged into g, it gives us 2, and then that 2 plugged back into f of x will give us 9. Also note that, again, f composed with g and g composed with f did not give us the same things. So again, talking about that order a little bit, Recall from section 0.1.5 that both addition and multiplication are commutative, while subtraction and division are not. Namely, when we add, what does this mean for functions? What it means for plugging into the addition, the sum doesn't really matter, nor does the product. However, the difference does matter because you don't get the same thing, and the division, you don't get the same thing. We actually saw that in the last video. We computed, so we did a couple examples with that. Also, as we've seen in the last two examples now that we've worked, composing g with f does not necessarily give you f composed with g. Namely, g of f of x does not have to equal f of g of x. So in other words, the big fancy way of saying this is that function composition is not commutative. One last thing, as far as the domain of a composition, it's going to be the set of all x in the domain of g such that g of x is in the domain of f. Again, this picture essentially tells you, here you have the domain, you have all your x in the domain of g, but then there's a chance that maybe you sort of have the range of g out here, but then f is only defined for a few of those. Namely, here, so this would be sort of the domain of f in here. Well, then we then have to, in order to get over to the range of f, we would need to make sure that we only take values from here and not that all got put over here. So that, in other words, there's only going to be some smaller set in here. So in practice, how do we do this? Well, let's go ahead and find the domain of these two functions. It's easier just to calculate out and then see what the domain is. Namely, we expect here the domain to be all real numbers, so we don't really need to worry about anything here. But here we see that we need the domain to be between -3 and 3. Namely, because we need 9 minus x squared to be greater than or equal to 0. Okay, which means x is going to be between -3 and 3. Good. So in other words, if we go through and we actually calculate this out, we would see f composed with g of x equals f of g of x. So it's interesting because when we do that, we end up with f of g of f of 9 minus x squared, square rooted. But then we go ahead and we square that, so we'd have f of 9 minus x. Well, so take that, square it, squared minus 9. Which gives us, squaring that kills off the square root, and we get 9 minus x squared. And so, minus 9, in other words, we would just get negative x squared, which is interesting because its domain, though, which is what we wanted, is still this, however. So let's have you do an example. Find the domain of f of g, f composed with g for the functions f of x equals square root of x and g of x equal x squared plus 4. On the count of 3, I'll reveal the solution. 1, 2, 3. So here we really need x to be any real number. X can be any real number because that's the domain of g. But then we need to make sure the domain of g falls into the domain that the range of g, that g of x falls into the domain of f of x. See the last slide. Namely, here we need x to be any real number, and g of x needs to be greater than or equal to 0 because that's the domain of f. But taking that, we see that x squared plus 4 is actually always going to be greater than or equal to 0 because x squared is always positive. So we have all real numbers as our domain, or negative infinity to infinity. This is clear also from looking at f composed with g of x. Namely, f composed with g of x is square root of x squared plus 4, which has the domain all real numbers. For more practice and working with function composition, be sure to see pages 81 and 82, numbers 2, 29 through 42, 43 through 44, and 47 and 48. In our next video, we're going to start talking about inverse functions.